In this video, I'm going to present our KIG3008 assignment, and for our project, we are making smart agriculture soil monitoring system. So our team consists of 4 members. The first one is Gilfred as the leader, Imanul Zulkarnayan, Hadif Harry, and Amirul Hakimi. So, in this section, I'm going to introduce a little bit about our project. In modern agriculture, efficient water management is vital. Traditional manual monitoring of soil moisture is often inconsistent, leading to a wasteful overwatering or harmful underwatering. Adding to the challenge, crucial sunlight exposure, which affects soil drying, is rarely measured, making irrigation decisions subjective and unreliable. This project introduces a low-cost smart agriculture soil monitoring system by integrating real-time soil moisture and light intensity data. It enables precise, informed irrigation, and this supports a healthier plant growth and sustainable water use, aligning with the goals of modern smart agriculture. As our problem statement, small-scale farmers often rely on manual observation to decide when to water plants, a method that is inaccurate, inconsistent, and time-consuming. This leads to overwatering or underwatering, which negatively impacts plant growth and crop quality. Additionally, light intensity, an important factor influencing soil moisture and plant water needs, is rarely measured. Without real-time data on soil moisture and sunlight exposure, farmers struggle to make precise irrigation decisions. Therefore, there is a need for a simple, affordable, and automated system that continuously monitors these conditions, provides timely feedback, and supports efficient watering practices for healthier plant development. Now we're moving on to the objectives of our project. There are 5 different objectives to be achieved by the end of this project. The first one is to design and build a soil moisture monitoring instrument using at least 2 sensors. Next, to measure and detect soil moisture levels accurately to support healthier plant growth. Number 3, to integrate a light intensity sensor, LDR, to study its effect on soil drying rates. Number 4, to apply instrumentation methodology, including hardware selection, electrical interfacing, and signal conditioning, system integration, and software development, which is Arduino. Last but not least is to test the system under real conditions and evaluate its accuracy. Now we're moving on to the methodology of our project. There are 7 steps in our methodology. The first one is problem identification. Traditional and small-scale farming relies on manual observation for irrigation decisions. Irrigation based on judgment often leads to overwatering or underwatering. Overwatering causes water wastage, while underwatering affects plant growth. Light intensity is rarely monitored, making it difficult to assess conditions affecting soil moisture. An automated and data-driven soil monitoring system is therefore required. Next step is the system requirement analysis. The system requirements were defined after identifying the problem. The system was required to measure soil moisture and light intensity in real time. The system was designed to be low cost and easy to use. Hardware requirements included sensors, a microcontroller, and a power supply. Software requirements included data processing and display of sensor readings. The third step is hardware design and component selection. Hardware components were selected based on the system requirements. The soil moisture sensor was used to measure the water content in the soil. A light sensor was used to measure the light intensity. An Arduino microcontroller was used to process the sensor data and control the system. All components were connected according to the design circuit configuration. The fourth step is the software development and programming. The microcontroller was programmed to read data from the soil moisture sensor and the light sensor at regular intervals. The software processes the sensor values and display the sensor readings. Threshold values were set to indicate whether irrigation is required based on soil moisture and light intensity conditions. The fifth step is the system integration. The hardware and software were integrated into a single working system. Sensor data acquisition, processing, and output were tested to ensure proper communication between components. Adjustments were made to improve the system accuracy and stability. The sixth step is the testing and calibration. Calibration was performed to improve measurement accuracy and reliability. The system was tested under different soil moisture and lighting conditions. Test results were compared with actual soil conditions to verify system performance. Lastly, or the seventh step, is the data analysis and evaluation. The collected data was analyzed to evaluate the system effectiveness in supporting irrigation decisions. The system ability to reduce water wastage and provide consistent monitoring was assessed. Possible improvements were identified for future enhancements for the system. Now we're moving on to the hardware selection. The first one is soil moisture sensor. The type that we are using is the capacitive soil moisture sensor version 1.2. It measures soil water content using capacitance, higher moisture, higher capacitance to an analog voltage output. This type of sensor is selected because corrosion resistant and more durable than resistive sensor. The next one is light intensity sensor. We are using LDR module. Resistance decreases as light intensity increases. It uses voltage divider to produce analog output, and it is selected because sunlight affects soil drying rate and watering needs. And lastly, our microcontroller, we are using Arduino Uno. It reads analog data from sensors using built-in ADC, low cost, open source, and easy to program. It is selected because it's suitable for simple prototyping and sensor integration.
So this is the circuit diagram for our project. All of the components is connected to a common 5-volt and ground into the microcontroller. The LCD contains SDA to connect the data and SCL for to sync the time with the built-in slots from the microcontroller. Basically, the process is the microcontroller will supply the 5 volt to these two sensors, which in return give a signal to A0, and the LDR will give a signal to A1. Then the microcontroller reads this data and sends the data to the LCD to display.
So this is the flowchart of our project.
So this is the setup with all the components. We can see the value of the soil and light intensity level in the LCD. In order to determine it works, we will turn on the light so that it can detect the light change and we can see the value changes.
For testing and data collection, for each sensor, several tests is done to determine the reliability of the prototype in real-world scenarios. Below are the reading results under different conditions. So the first one, this is the result of voltage level and percentage on dry soil and no light conditions. As you can see, the soil is 0% and the light is 0%. The next one is the voltage level and percentage on wet soils and bright light conditions. As you can see, soil is 24% and the light is 97%. As the procedure, the Arduino microcontroller was connected to the soil moisture sensor and the light intensity sensor according to the design circuit configuration. Number two, a pot filled with soil was prepared for the testing process. Number three, the soil moisture sensor was submerged into the pot and the initial readings of both the soil moisture sensor and the light intensity sensor were recorded. The soil moisture sensor readings were recorded at increasing time intervals while the light intensity sensor reading was maintained constant. Lastly, the test was repeated under different light intensity conditions by varying the surrounding light environment and the corresponding sensor readings were recorded for comparison. So in this section, we're going to discuss the result and analysis. The first one is soil moisture readings over time. This is the table that we have obtained from our own experiment and also the graph that we have plotted, which is the graph of soil moisture versus time in minutes. And from this graph, we can observe that the soil moisture percentage decreases gradually with time. This indicates that the water content in the soil reduces due to evaporation and absorption by the soil. Now we're going to discuss about the effect of light intensity on soil drying. So the purpose of this experiment is to study the effect of sunlight on soil drying. Soil moisture readings were compared under different light intensity levels. So this is the table that we have obtained. As you can see, higher light intensity results in a faster reduction of soil moisture. Under high light conditions, evaporation occurs more rapidly, causing the soil to dry faster. So as for the discussion of this project, the first one is the system performance. The system operated reliably during testing. The soil moisture sensors detected changes in water content accurately, and the LDR sensor responded consistently to different light conditions. The Arduino processed and displayed real-time data for continuous monitoring. Next is the challenge we encountered during our project, which is such as minor fluctuations were observed in sensor readings due to soil movement, compaction, and lighting changes. Calibration accuracy was affected by soil type, density, and water distributions. Next is the benefits of combined monitoring. Soil moisture data shows current water levels, while light intensity helps predict drying rates. Combining both improves irrigation decisions, reduces water wastage, and supports healthier plant growth. And lastly is the sensor limitations. The soil moisture sensor provides relative measurements influenced by soil conditions and placement. The LDR sensors indicates relative light intensity rather than exact lux values. Now that we have reached the end of the presentation or video, it's time to conclude our project. This project successfully developed a low-cost smart agriculture soil monitoring system using a capacitive soil moisture sensor, an LDR light sensor, and an Arduino microcontroller. The system reliably monitors soil moisture and light intensity in real time, enabling better irrigation decisions by considering both current soil conditions and drying rates. By reducing reliance on manual inspection, it helps prevent over and underwatering, minimizes water wastage, and promotes healthier plant growth. This system is suitable for small-scale agriculture, home gardening, and educational applications, with future improvements including automated irrigation, more precise sensor, and wireless monitorings. That is all for our team. Thank you very much.